Black holes are among the most fascinating objects in the universe. They captivate our imagination and challenge our understanding of the cosmos. They are regions of spacetime where gravity is so strong that nothing, not even light, can escape. This immense gravitational pull creates a boundary known as the event horizon. Imagine a place where the fabric of space and time itself is being pulled inwards, creating a cosmic abyss from which there is no return. This warping of spacetime is a direct consequence of the black hole's intense gravity. This is the essence of a black hole, a region where the known laws of physics are pushed to their limits. Black holes form when massive stars collapse at the end of their lives. This collapse is often marked by a spectacular supernova explosion, which can outshine entire galaxies for a brief period. These stellar remnants are incredibly dense. A single teaspoon of this material would weigh billions of tons on Earth. Their gravitational pull is so immense that they warp the fabric of space-time around them. This warping can bend light and distort the appearance of objects behind them, a phenomenon known as gravitational lensing. This warping is what creates the event horizon, the point of no return for anything that ventures too close. Once an object crosses this boundary, it is inevitably pulled into the black hole. The existence of black holes was first predicted by Albert Einstein's theory of general relativity. His equations suggested that under certain conditions, space-time could collapse into a singularity. However, it wasn't until much later that astronomers were able to observe their effects indirectly. By studying the motion of stars and gas clouds, they could infer the presence of these invisible giants. Today, we have evidence for the existence of black holes of various sizes. From stellar mass black holes formed by collapsing stars to supermassive black holes at the centers of galaxies. Some are just a few times the mass of our Sun, making them relatively small in the cosmic scale, while others, known as supermassive black holes, lurk at the centers of galaxies, containing millions or even billions of solar masses. These behemoths can influence the formation and evolution of entire galaxies. These cosmic giants play a crucial role in the evolution of galaxies like our own. They can regulate star formation and even shape the structure of the galaxy itself. To understand black holes, we must first delve into the realm of Einstein's general relativity. This revolutionary theory, published in 1915, forever changed our understanding of gravity. Einstein proposed that gravity is not a force but rather a curvature of spacetime caused by the presence of mass and energy. Imagine a bowling ball placed on a trampoline. The ball creates a dip in the fabric, causing nearby objects to roll towards it. This is a simplified analogy for how gravity works in general relativity. Massive objects like stars and black holes warp spacetime around them, creating a gravitational well that pulls in everything within its reach. Black holes represent the most extreme manifestation of this warping. Their immense density creates a gravitational singularity, a point of infinite density and zero volume at their center. Surrounding this singularity is the event horizon. This marks the boundary beyond which the gravitational pull is so strong that escape is impossible. Even light, the fastest thing in the universe, cannot escape the clutches of a black hole once it crosses this boundary. For a long time, black holes were thought to be completely black, eternally consuming matter and energy with no possibility of anything escaping. However, in 1974, physicist Stephen Hawking made a groundbreaking discovery that changed our understanding of these enigmatic objects. He theorized that black holes are not entirely black after all. They actually emit a faint thermal radiation, now known as Hawking radiation. This radiation arises from quantum mechanical effects near the event horizon. According to quantum mechanics, empty space is not truly empty. Instead, it's teeming with virtual particle-antiparticle pairs that constantly pop into existence and annihilate each other. Hawking realized that if such a pair were to form near the event horizon of a black hole, one particle could fall in while the other escapes into space. The escaping particle carries away some energy from the black hole, effectively reducing its mass over time. This process is incredibly slow, especially for large black holes. However, it has profound implications. It means that black holes are not eternal prisons. They eventually evaporate, albeit over incredibly long time scales. Section 4. A cosmic paradox, black holes, and the third law. Hawking's discovery of black hole radiation introduced a fascinating paradox when considering the laws of thermodynamics, particularly the third law. This discovery was groundbreaking because it challenged our understanding of how black holes interact with the universe and the fundamental laws that govern it. The third law of thermodynamics states that the entropy of a system approaches a constant value as its temperature approaches absolute zero. In simpler terms, as things get colder and colder, their disorder, or entropy, decreases and eventually stabilizes. Entropy is a measure of disorder or randomness within a system. In the vast and chaotic universe, entropy is a crucial concept that helps us understand the direction of natural processes. Black holes, as we understand them, pose a challenge to this law. They are regions of space where gravity is so strong that nothing, not even light, can escape from them. As matter falls into a black hole, it seemingly disappears from our observable universe. This disappearance raises questions about what happens to the information and entropy associated with that matter. This process appears to decrease the total entropy of the universe, violating the second law of thermodynamics, which states that entropy always increases in a closed system. The second law is fundamental to our understanding of time and the evolution of the universe. However, the existence of Hawking radiation suggests a resolution to this paradox. Hawking proposed that black holes are not entirely black, but emit radiation due to quantum effects near the event horizon. As black holes emit radiation, they lose mass and eventually evaporate completely. This process, known as black hole evaporation, implies that black holes have a finite lifespan. This evaporation process increases the entropy of the surrounding universe, compensating for the apparent decrease caused by matter falling into the black hole. Thus, the overall entropy of the universe continues to increase in line with the second law of thermodynamics. Furthermore, Hawking radiation implies that black holes have a temperature, which is inversely proportional to their mass. This means that smaller black holes are hotter and emit more radiation than larger ones. This means that as a black hole loses mass through Hawking radiation, its temperature increases. The hotter the black hole, the faster it loses mass, leading to a runaway process of evaporation. This relationship between mass, temperature, and entropy suggests that black holes, despite their exotic nature, might adhere to the laws of thermodynamics after all. The interplay between these factors provides a deeper understanding of the universe and the fundamental principles that govern it. Section 5. The zero-point enigma, extremal black holes. Within the realm of black hole physics, there exists a particularly intriguing theoretical concept known as extremal black holes. These objects push the boundaries of our understanding of the universe and challenge the very limits of physics. These hypothetical objects represent the absolute limit of how much charge or angular momentum a black hole of a given mass can possess. In essence, they are the most extreme forms of black holes that can theoretically exist. What makes these theoretical objects so fascinating is the possibility that they could exist at absolute zero temperature. This means they would be devoid of any thermal energy, a state that is incredibly difficult to achieve and maintain. This concept arises from the relationship between a black hole's mass, angular momentum, and charge, as described by the no-hair theorem. This theorem simplifies the complex nature of black holes into three fundamental properties. This theorem states that black holes can be completely characterized by only three externally observable properties: mass, electric charge, and angular momentum. All other information about the matter that formed the black hole or is falling into it is lost behind the event horizon. All other information about the matter that formed the black hole or is falling into it is lost behind the event horizon. This makes black holes incredibly mysterious and difficult to study. Extremal black holes sit at the very edge of this theorem. They possess the maximum possible charge or angular momentum for a given mass, making them unique and extreme in every sense. They possess the maximum possible charge or angular momentum for a given mass. Any further increase in these properties would cause the black hole to violate the laws of physics as we understand them. Any further increase in these properties would cause the black hole to violate the laws of physics as we understand them. This makes extremal black holes a fascinating subject of study for theoretical physicists. At this extremal limit, theoretical calculations suggest that the black hole's temperature would reach absolute zero, the lowest possible temperature theoretically attainable. This state of zero thermal energy is a concept that intrigues scientists and challenges our understanding of thermodynamics. However, The existence of extremal black holes, let alone their zero-temperature nature, remains purely theoretical. Despite extensive mathematical modeling and simulations, we have yet to find any observational evidence for these exotic objects. Observational evidence for such objects is currently lacking, and some physicists question whether they can actually form in the real universe. The conditions required for their formation are incredibly precise and may be impossible to achieve in nature. The conditions required for their formation are incredibly precise and may be impossible to achieve in nature. This leaves extremal black holes as one of the most tantalizing and elusive concepts in modern astrophysics, a topic that continues to inspire and challenge scientists around the world.